Today is going to be 63-1. We're going to take a look at the real zeros of polynomials. Now, because the transition is going to be, we're going to take a look at all the zeros of a polynomial, we're going to start off with the properties of complex numbers. So we're going to add, subtract, multiply, and divide complex numbers, and we're going to simplify complex numbers, as well as take a look at the conjugate. Now we know that the square root of a negative number is not a real number. Now the reason why is if I take the square root of that -1, well, the way that I would get that, or if I were to think backwards, is that is there a way for me to get a -1 in this type of format? If I take something and square it, can I get a -1? Can I, like 1 squared, well that equals a +1, and -1 squared, well that also equals a +1. And so because there is no real number x that's going to satisfy this situation, that's why it's not going to be a real number. And so what we do instead is we say, instead of the square root of -1, we're going to let that be I. And if I square this, then I squared, the square root and the square cancel out, so I get I squared is going to be -1. Now the reason why we use this notation is it's kind of easier. I mean, like, writing out the square root of -1 over and over and over again, it starts to become tedious, and also we're able to express it in a certain format, which we're going to talk about eventually, and that certain format eventually in math, as you go higher in math, has certain properties that apply to it. And so here it says express each number in terms of I. So the square root of -7, I want to break that apart into the square root of -1 and the square root of 7. And then that we said was I, so it's going to be I root 7. Now it is better to write it in this format. Okay, so even though that's I and that's root 7, it is better to write it in this format, and we're going to talk about that shortly. For this one, that's going to be the square root of -1 and the square root of 16. That is I. That is a 4, and so the better format to write it is going to be 4I. Now a lot of us get confused and we think, oh, I need to distribute that -3. You can't do that, so that negative stays, and then this, we get the square root of -1 and then the square root of 13. We still have a negative, that becomes I, that becomes root 13, and so the way that I would write it would be -root 13I. The I is always going to be at the very end. And this one, we are going to have to continue to break it, so I still have to do that square root of -1 and the square root of 48, but then that square root of 48 I can break down further. That'll turn into square root of 16 and square root of 3, that'll turn into a 4. So this is an I, this is a 4, and this is a root 3, and so the better way of writing it is going to be this 4 root 3I. Now a complex number is a number of the form a plus bi. So this is the format in which I want to write my complex numbers, where a and b are going to be real numbers. And the real number a is said to be the real part of a plus bi, and the number b is said to be the imaginary part of a plus bi. And so every single time that we manipulate, simplify complex numbers, we want to write it in that form of a plus bi. So complex numbers, they're actually going to obey the commutative, associative, and distributive laws. And so because of that, we can add like terms together. So 8 and 3 combine into 9, 6i and 2i combine into 8i. For here, I can distribute that negative through. And so I'm going to get -6 and 3, positive 3i. So 4 and -6 give me a -2. A 5i and a 3i, that's going to give me an 8i. Now remember, we do have to write it in that a plus bi form, so a plus bi, a plus bi. Now when we multiply, we need to remember that I squared equals -1. So if we ever get an I squared, we need to simplify that further by changing that into a -1. Now all distributive properties follow suit. So 1 times 1 is 1, 1 times 3i is 3i, 2i times 1 is 2i, 2i times 3i gives me 6i squared. I can combine the 3i and the 2i together. The I squared we said is negative 1. So that became 5i. That became a negative 1. 6 and negative 1 gives me a negative 6. So then the 1 and the negative 6 gives me negative 5. And so I'm left with negative 5 plus 5i. This right here, this is going to be the a plus bi form. Now this, remember, we don't take the square and multiply everything through. This says I have 2 of these. So here are my 2 of those. And now I can take this and I can distribute it through. So 3 times 3 is 9. 3 times negative 21, so I get negative 21i. Negative 7i times 3, negative 7i times negative 7i gives me 49i squared. Now this I squared, that's going to be negative 1. And so that's going to turn into negative 42i. So 49 and negative 1, that becomes a negative 49. So 9 minus 49 becomes negative 40. And so negative 40 minus 42i. I have that a plus bi form. Now we're going to look into how do we simplify i's as it keeps getting raised to a higher and higher exponent. And so it's a very high power. Now we have to follow a pattern. So we know that I is the square root of negative 1. We defined that, which meant that I squared is going to be negative 1. Well, what is I cubed? Well, I can break that apart into I squared times I. I squared is negative 1. I still have my I, so negative 1 times I gives me negative I. Now I to the 4th power, I can say that that's going to be I squared squared. I squared is negative 1, so negative 1 squared is going to be positive 1. Now one thing you're going to notice is after we get to that I to the 4th, every single time I can break it apart into some version of I to the 4th. Now if I do that, that's going to leave me with an I squared, I to the 3rd, I to the 4th type of pattern. And if you notice, it repeats. I, negative 1, negative I, 1. Now because it's cyclic by that pattern of 4, there's a shortcut that we can use. And so if I divide 4 into that power there, what's going to end up happening is I interpret my remainders. Now if my remainder is 1, it's going to just be I. If my remainder is 2, it implies that it's I squared, which means it's going to be negative 1. If my remainder is 3, it's going to be I to the 3rd power, which is going to be negative I. If my remainder is 0, it's going to be I to the 4th power, which is just going to be 1. So let's try that. So I have I to the 37th power. So that means we said with the shortcut, if I divide 4 into it, my remainder is 1. So interpreting this, if my remainder is 1, I know it's going to just be I. Now the reason being is I said that I can break it apart into I to the 4th power because these are just turned into 1s. Well, I can get 9 I to the 4th powers. There's 9 of them that are in there because 4 times 9 is 36, 36 plus 1. And so we know that this I to the 4th power is 1, so 1 to the 9th is just 1. 1 times I gives me that I. To find B, take that 58, and I need to divide that, or divide 4 into 58. I'm going to get remainder 2. Remainder 2 we said is I squared, so it's going to be negative 1. Now talking about the conjugate. The conjugate of a complex number a plus bi is going to be a minus bi. Now the numbers a plus bi and a minus bi, we consider those or call those conjugate pairs. So each of the following pairs, or following numbers, we consider these conjugate pairs here. Okay, so each of these are going to be conjugate pairs. A plus bi, a minus bi. 14 minus 5i, 14 plus 5i. Notice that this number here, that's the number that changes. Now this one, these are conjugates of each other because we have to classify this as 0 plus ai and 0 minus ai. So a plus bi, a minus bi. And so those are going to be conjugates of each other. Now there's an important aspect to these conjugates, and we're going to discover it right now. What happens when I multiply conjugates together? And it's actually kind of cool. So we know that these are conjugate pairs here, right? A plus bi, a minus bi. Now if I multiply these together, 5 times 5, 25, 5 times negative 7i, multiply, multiply. So if I multiply all those together, now notice what happens. First of all, this cancels out, and we know that I squared is going to be negative 1. Negative negative is a positive, and so I'm going to get 74. Where are my imaginary numbers? Well, they're gone. So whenever you multiply by a conjugate, when it comes to imaginary numbers, they disappear. Now in general, if you multiply by the conjugate of anything that's a square root, the square root value will disappear. So if we're considering I being the square root of negative 1, well, I don't have that anymore. Now a way that we can quickly do this, you don't have to do this, you can do everything out like we just did here, do, and you get your 74. But this is like the difference of squares, a plus b, a minus b. And so because of that, the difference of squares says that's just a squared minus b squared. So a plus b, a minus b, that's just going to be a squared minus b squared. And so simplifying that, you end up getting 74 as well. So it's just something that's just a little quicker. You don't necessarily have to do it that way, but it's just a little quicker. So in this case, if I wanted to simplify this radical here, this radical here in the denominator, whenever we have rational values, just know that it's improper for us to have a radical in the denominator. And so if I wanted to rationalize it or get rid of that I, we said that the shortcut or the secret is if you multiply by the conjugate, all radicals will disappear in there. So the conjugate of 1 minus 6i is going to be 1 plus 6i. Now the way you need to envision this is those have parentheses around them, which means that this is going to be a type of FOIL. So 2 times 1, 2 times 6i, negative 5i times 1, negative 5i times 6i, over 1 times 1, 1 times 6i. Now remember, the inner and the outer part, that's going to cancel out. So technically you could just focus on the first and the last, but that's okay. Now I need to simplify, so this will turn into 7i, this will cancel out, those will turn into negative 1s. Negative, negative, positive, negative, negative is a positive, and so 2 and 30, 1 and 36. Now a lot of us sometimes we think, okay, we have this, we are done. And the answer is, you are not done. Remember we said that complex numbers have to be in the form a plus bi. So I need to leave it in the form a plus bi. So this is going to be a plus bi. And so there's my form. You just basically break that 37 into both of these terms. So now it's in that form of a plus bi. And this would be the answer. Now looking at conjugate notation. Sometimes it's much easier for us to represent conjugate notation and by using the conjugate notation. And the way that we represent that is through this bar. So if I have some a plus bi and I draw a bar over it, what that's saying is this is the conjugate of a plus bi. So for example, the conjugate of 3 plus 2i is 3 minus 2i. The conjugate of 3 minus 2i is 3 plus I. The conjugate of 6 is going to be 6. Now the reason being is, remember we said that this is a plus bi. Well, that's a 0. So I have 6 plus 0i. Well, the conjugate of that is 6 minus 0i. 6 and 6. Those are the same. And likewise with the 4i, the conjugate of 4i, because I have 0 plus 4i, well, the conjugate of this would be 0 minus 4i, and so that's why I have my minus 4i. Now, a few other properties to take a look at. The first is z bar bar is going to be z. Now it's kind of like, wait, what? Why is that? Let's look at an example. Well, if I have 1 plus I, if I take 1 bar of that, that gives me 1 minus I, which means that if I take the bar again, that means that that's technically saying, hey, take the conjugate of that, And if I take the conjugate of that, that gives me back to 1 plus I. So we start with 1 plus I. If I take the bar of it, it gives me that. Well, if I take the bar of this, right, imagine there's a bar of that, then that's going to give me that, which simplifies back into the 1 plus I. The other properties that it says that if I take the conjugate of z and add that to the conjugate of w, it's the same as if I added them together and then took the conjugate of it. This one is stating if I take the conjugate of z times the conjugate of w, it's as if I multiplied them together first and then took the conjugate of it. This is saying if I take the conjugate of z to some power, it's the same if I took z to some power and then took the conjugate of it. And z is a real number if and only if the conjugate of z is z. And this is the perfect example of that. This is a real number if I take the conjugate of this, it gives me the same value. And we know that 6 happens to be a real number. All right, so let's use that notation. If I know that z is 1 plus 3i, what is z times z bar? Well, my z is going to be 1 plus 3i. We said z bar means the conjugate of, so 1 minus 3i. I know that we know how to multiply and simplify that together. And this one says z bar squared. Well, this is saying that take the conjugate of z squared. Well, the conjugate of z is 1 minus 3i. Square that. And I know you guys know how to multiply that all through. So this is z times z bar, and this is z bar squared. Well, this does conclude our lesson. If you guys do have any other questions, please leave them in the comments.